Dispersion. All right, I'm going to stop it. So nice to hear songs about MRI. The reason I did mention it because it has the phase component in MRI that plays a big role. Welcome to Lecture 30, EE123, Lecture 30. Woo! This is our 30th anniversary. And we have just a few more to go, and then we're going to get divorced. Sad for who? No, I'll be sad to see you go. So today I did promise that we're going to talk about Lab 6 and the project, but I lied. We're just going to talk about Lab 6. The projects we're going to talk about on Friday. Okay? It was either the projects or taxes. And so it's taxes. Projects on Friday. I wanted to finish the demo to show you some of the, basically the basic approach, and not ready, sorry. So on Friday we're going to talk about possibility of projects. But one of the things that seems to come is basically it's an open project, not as opposed to previous years where we had kind of like a more constructed. Now it's going to be more open, in the sense that you need to take an image and communicate it, and I don't care how you do it. Okay, and you need to communicate it as fast as possible with the highest quality. Okay, that's the task. That will be the default project. And you can do that, of course, with the radio. Not by like compressing it and running, okay, and then installing it on a different computer. That would not work. Okay, so with the radio, and you can do that either digitally or you could do it in analog way. If it's analog, there's going to be one restriction: is not to use previous projects. Okay, so no Martin M1 SSTV protocol. Okay, so that was the 2-year, the projects in the previous 2 years. That will not be allowed. Okay, but you can do something else. And I think that actually gives you a lot of leverage in what you could do. In particular, you could leverage Lab 6, which will be creating some sort of a modem. And you can improve upon this modem by signal processing. You can compress the image if you want. You cannot use external software to do this. You have to do it by yourself. And I think you'll learn quite a bit from this. But it gives you a little bit of a head start. The fact that you have some default idea that you can either leverage or come up with your own. Okay, so this is what coming. But I'll give you also some other suggestions for projects that are possible. For example, one of them is creating what's called a bistatic passive radar. So if you take 2 SDRs and you aim an antenna towards, let's say, a radio station, and aim another antenna connected to a different SDR the other way, you can use the radio station as a source for radar and be able to catch reflections coming, for example, airplanes, meteors actually, and things that are in the sky. And you do that, very similar to Lab 2 or 1? The sonar one. Yeah, Lab 1. In a very similar way, but you will have to kind of use that with 2 software-defined radios. They have to a little bit figure out how to synchronize them, but I think it should be quite fun. Another option is using 2 SDRs to do what's called a phase array receive, where you have 2 or 3 antennas connected to 3 SDRs, and you basically electronically steer the direction that these antennae look at by complex adding the signals coming from the SDR. So it's kind of like phasing the antennas. So that's also a really cool project. You can perhaps even figure out location from sources using this. There's some challenges because two SDRs are not have the same clock. There's certain delays that you have to figure out, filtering and so on and so forth. So this is quite a nice project, I think. And those are two that I really recommend if you're not going to do the default one, which is the image communication, which is also very cool. Okay, so sending images as fast as possible. If you can do video, you get an A. All right. Well, was I recorded? I guess so. Delete. I don't know if you get an A, but you get an A for the project. Okay. All right. So any questions, by the way? So everybody, we're good on lab 5? Yeah. Anybody not so good? Everybody were able to transmit? Send their call sign with what's the name for Morse code? Yeah, CW. No, not everybody. Those that don't, please see me after this. We'll have to figure out a solution for you. Okay. Yeah, Lab 6. I want to talk about Lab 6. So now we're getting to, Lab 6 is I'm super excited about this. Like every time I go back and actually go and have to tinker with it, it's like, wow, that's cool. All right, so the idea in Lab 6 is we teach you a little bit about digital communication. Okay, so you've got the pre-lab part that you're going to go through. And the pre-lab shows you some concepts in digital communication. For example, amplitude shift keying is the most simple way of sending digital communication. Is either on or off. Okay, so it's also called OOK, on-off keying. Okay, you either transmit a certain frequency or you're not transmitting a certain frequency in a period of time, and that translates to digital bits. You can do that either by encoding transitions, like ADS-B was. You remember with the airplane ADS-B airplane radar that we did in Lab 3 or 2, Lab 2. It uses on-off keying, but it uses it in what's called a Manchester coding, where the transition from high to low was encoded as bit 1, and from low to high was coded as bit 0. Okay, that's another way to encode information. Okay, by transitions. Okay, but spectrum of OOK, of course, is not very narrow because these are rectangular pulses. Okay, so you're going to look at this. You're going to compute the spectrum. And what you could do in order to make the spectrum a little bit more narrow, and so prevent signal to leak to other frequencies. Window it with what? So what if the on, window is a good one, but what if the on part was really a band-limited pulse, and the off part was just not? Okay, then we're going to be almost guaranteeing that the signal is going to be band-limited. Okay, so this is called pulse shaping, and effectively you can replace each one of these on pulses, okay, with a windowed sink. Okay, so if you think about this, instead of having a rectangular window, I have a windowed sink. Okay, so each one of them is a windowed sink, and you can decide what is the time bandwidth that you're going to pick for this particular pulse. Okay, so that's going to tell you how long you're going to extend it, and that's going to tell you how much leakage it's going to have in the frequency domain. So this is replacing this with a shaping those pulses with band-limited. Shaping them as band-limited pulses. And in that case, what we get is now the spectrum becomes almost band limited, right? It's never going to be completely band limited because we cannot play this pulse forever. We're going to decide, yeah, you're going to be time bandwidth 4. In this case, it was actually time bandwidth 4. Okay, so then you see kind of almost the shape of the time bandwidth 4 around 1800 hertz in this case. Now, what did we win? We won some narrow bandwidth. Now there's no leakage of energy to other frequency bands, so that satisfies a lot of constraints in communications. So when you have multiple users, you want to allocate maybe a frequency for each user, then they don't leak to each other. The problem here is what we did lose is, so we started having is inter-symbol interference. What does that mean? If you think about this, this is the point where we decide this is bit, this is on, okay? But before, when we had these rectangular pulses, the entire thing was on for a certain time. So if we have certain delays in the, on our receiver, it's not a big deal, okay? It's still on, okay? So any delays here, I would, let's say, evaluate over here or evaluate here, it doesn't matter, it's still going to be on. So delays is not going to play a big role. Here at this point, yeah, it is on, and here at this point, it is off. But if I'm a little bit delayed, I'm getting interference from the previous symbol. This is what's called inter-symbol interference. So I gained band limitedness, I lost in inter-symbol interference. Okay, there's always these trade-offs. Okay, now if my system is delayed by that much, then oh boy, I've got a lot more inter-symbol interference. Yes.
Let's say we didn't need to transmit a ton of different users. Would it be okay if we were wideband?
Well, the question is are you using your bandwidth efficiently, right? And that's the real question, right? And this is on-off keying is not an efficient use of bandwidth. Okay, it's a simple one. And you'll see that for chips that communicate, let's say, at 256 gigs, like short range communication. So all the IC that people are making, often they choose these type of communication protocols because they can go so fast anyway at those rates. The spectrum, and because you want to save energy in terms of computation on those ICs, then you're going to trade off the spectral efficiency with, with power in terms of how much you need to calculate and make the encoding, decoding system more simple. Okay, so there's a lot of trade-offs that people come up with, and that really depends. If you're talking about the 2-meter band, that would be terrible, right? Because it's just 4 megahertz, just very small. The cell phone band, it's like heavily used. You want to be really careful about how you use bandwidth there. So this is one way to encode, right? On-off keying. By the way, one of the projects that you could be doing is on-off keying using your FM radio, because you can key it on, you can key it off. And you can use a SDR to receive, and then you can come up with these codes that have very narrow autocorrelation, much like, remember, we did with the lab one with the radar that we created a chirp. You can do something similar in on-off keying that has a narrow autocorrelation that will give you the ability to do weak signal communication. Okay, so you transmit this, code for a long time. Let's say over, tens of seconds, you transfer 1 bit or 2 bits, and then on the receiver end, somebody is going to do these autocorrelations and be able to detect them coming out of the noise. Okay. You can do that. There's a lot of use for these things in sensor networks. Like if you have a remote place where you're going to put, you're going to measure some telemetry, you need to slow data rates over long distances and a reliable one. That could be another interesting project. Okay, just room for thought. Okay, so this is narrow band but inter-symbol interference. Now this is encoding information in the amplitude. But binary information, the amplitude, either on or off. Okay. Another way to encode information is in phase. And a protocol called phase shift keying, or PSK. what it does, it encodes information in the phase. So at some point you either send a cosine or a negative cosine. Okay, this is binary phase shift keying. So for a certain length of a certain bit length, so you decide what the bit rate is going to be. Okay, the bit rate is 1 over the that time point. This is 1 bit length, so that also determines the bit rate. Okay, so you're going to send 1 bit over that time, and then another time, and another time, and another time. So here's I'll pass through 4 bits already. Okay, and the information is encoded in a phase. So for this, we've got a cosine with 0 phase, and this is a cosine with inverted, or actually that was probably a sine. This is a sine. Starts with a 0. So this is a sine, and this is an inverse sine, like minus sine. Okay, and you just switch between these two every bit. Okay, because they're orthogonal. Sorry, they're not orthogonal. But if you correlate now with the sine, you'll see basically it changes with a sinusoid function. At that frequency, you will get basically the sine back. Okay, if you look at the spectrum of this, looks like this. Again, it's because the phase. The signal is continuous, but it doesn't have a continuous derivative. Okay? So at this point, we're kind of like, we're going to switch. Okay, so the derivative is not continuous, and so that because of that creates again quite a wide bandwidth. This is really heavily used. Actually, one of the advantages of this compared, let's say, to this type of approach is that we're always transmitting. In terms of signal-to-noise ratio efficiency, we're always transmitting, all the time. Okay, so your duty rate in this case is only 50%, at least. And here it's 100%. So you're always transmitting. It's a lot more efficient in that sense. The other thing is that what's the envelope of the signal? It's constant envelope, right? So I can use a nonlinear amplifier. Yes?
Why is it more efficient to always transmit?
We're trying to detect signals, right? If you think of the best possible decoder would be to do a match filtering or a correlation with whatever somebody's transmitted. Okay? If the signal that you're transmitting is always transmitting, you integrate over the entire signal, so you get a higher signal out. It's basically the power per unit time that you're transmitting. Right?
Okay, so like the efficiency in receiving, not efficiency in sending.
Well, it's both. Right? Well, you're using more power to transmit. That's correct. Yeah, you're using more power. But if you actually look at per unit time, how much you're transmitting, this is more. This gets you more for the same system. Okay, you get 50%, like 100% more power transmitted using this system. It has a constant envelope. That means that we can use a nonlinear amplifier when amplifying that kind of a signal. For amplifiers, it's much easier to track the phase than to track the magnitude. Okay, to track the phase, it doesn't have to be linear, and so amplifiers can be way more efficient in this type of a scenario. Okay, so that's very nice. The spectrum is kind of lacking. Now, this is binary phase shift keying, but of course you could do more phases. Okay, for example, I could use also a cosine and a negative cosine, and that will be QPSK, quadrature phase modulation. Okay, quadrature phase shift keying, where I'm going to use 4 phases. Or I can divide the entire unit circle into places along the, just break it into, let's say, 8 different phases and transmit those. Right? So I can do an Emery type of phase shift keying, where I'm going to then correlate with my signal back, detect what the phase was, and if the phase, let's say, if I'm breaking it into 8 parts, I'm going to look at which is the right one, and then translate into bits. Okay. So this is phase shift keying in incorporating information in the phase. If you actually go back to amplitude shift keying, yeah, I can send also an Emery type of a signal if I have going to have two different types of amplitudes. Okay, I can say, well, if I have an amplitude that high, then that's going to be, 1, 1, 2 bits. And then half of that would be another set of bits, right? And then so on and so forth. So I can break from 0 all the way to a certain amplitude. I can break that into more bits. And I can get more throughput. Okay? What would be the issue, though? With an Emery type of... let's say I sent you just a single, I keyed with a certain amplitude. Now it gets to you. Is it 0, 1, 2, or 3? You have to normalize. What's the maximum, right? And if you've got fading due to atmospheric condition, different pathways, that's going to be a problem, right? And what happens when you have noise? Let's say there's a spike noise that puts exactly at the time that what I'm transmitting, puts an extra spike there, right? That could be a problem. Okay, that can throw me between. I can get basically more errors that way. So I'm adding more throughput at the same time I'm making my system more sensitive to errors. Okay, so we talked about amplitude. You're going to see encoding binary digital information in phase. We can, in a similar strategy as we did for the amplitude, we can also pulse shape phase shift keying by, again, having a time bandwidth, let's say, for a signal that has a particular phase, either a positive phase or a negative phase. In that case, my signal is going to look like this. Okay. In this case, you have 1, and then a 0, and a 0, which is here, and then a 1, another 0, and another 1, and so on and so forth. In the case where you switch the sign, you'll see that the signal is actually going to cancel at some point, right, between these two. Because you have different phases, so if you have some signal that leaks, you have this inter-symbol interference now between the two, and that's going to cancel at some point. Okay, so the bandwidth is nice. However, what happens? What do we lose now? The constant envelope that we lost, right? We used to have a constant envelope. Now we have to use a more linear amplifier, okay, in order to be able to maintain this bandwidth. Okay, so again, this is another trade-off. Okay. Now, so we said that we can encode information in magnitude. Yes?
Yes, sir. You said you just lost the constant envelope with the slide so good.
It's not a constant envelope.
Oh, right.
It's not a constant envelope. We lost the constant envelope, and it's not a constant envelope. Similar.
Why is that important? That you can still amplify it non-linearly
But it will create distortions on the spectrum, right? So yes and no. Yeah, if we amplify it and that's not going to be a linear response, then we're not going to get this nice time bandwidth for sequence, and that's going to trade off some of the bandwidth. Yeah, it's always going to be this kind of a trade-off. So we talked about ways to encode, again, digital information, one in the phase, one the amplitude. And the question is like, why separate? Right? Why not encode in phase and amplitude? Right? We can do both. And this is what's called a quadrature amplitude modulation, or QAM, okay, where you break the complex plane into a matrix which has amplitude and phase, okay, and you're going to send, basically this tells you how much the quadrature component is the sine, the in-phase component is the cosine, and it tells you basically how much amplitude of that cosine and sine you're going to transmit for a 1-bit period. If I want to send the value 2, I would basically have this kind of phase with this kind of amplitude. If I want to send a value 1, I'm going to have that much phase and amplitude, and so on and so forth. Okay, this is QAM 16. This is called QAM 16. Your cable TV uses QAM 64 and QAM 256. Okay? So every bit period, you're actually transmitting, or every symbol period, they call it symbol period, you're transmitting a lot of bits. In this case, you're transmitting 16 bits. Okay? At a single symbol period. So you get more efficient. What is the issues? Of course, if I've got noise, that might push me to here. Okay, so it only works for good signal-to-noise ratio. Okay? So I can break that into, 512 by 512 if I wanted to, but of course noise is going to throw me away. Okay? That accuracy. So this is called QAM, and this is basically how it's going to look like. I'm going to transmit this series of bits, 6, 11, 0, 4. You see that these are symbols that are multi-bit. In fact, 6 will have that kind of phase and that kind of amplitude. 11, that kind of, it's the, opposite phase with the same magnitude. So let's see, 6 and 11. 6, 11 is C, right? B. Where's B? This one? Oh, I guess it was just 90-degree phase. And so on and so forth. And this bit over here, I think, was, let's say, 10. 10 is an A, right? Yeah. A is the highest amplitude, right? So you see the highest amplitude, okay, with a certain phase of 45 degrees, okay, between the sine and the cosine. Any questions? Yep.
Does POM 16, does it transmit 16 bits per symbol period, or is it 4 bits?
Sorry, 4 bits. 4 bits, that's right. QAM 16 transmits 4 bits. 64 transmits square root of that. Okay, so we encoded information in the amplitude. We encoded information in the phase. We encoded information in both. What else? Frequency. So we can do frequency shift keying, right? We can encode now information in the frequency. Okay, and this is called frequency shift keying. And frequency shift keying, or in binary frequency shift keying, we switch between two different frequencies. So on one bit period, we've got one frequency. On another bit period, we've got another frequency. In this case, we've got frequency 1200 hertz and 2400 hertz. At 300 bits per second, which is called 300 bauds. And at that rate, you've got 4 cycles, of the low frequency and 8 cycles of the high frequency. And the phase is going to be nice and continuous between the two. If I pick a bad choice of frequencies, the phase may not be continuous, or it's going to change considerably. Okay, so the phase may not start at every bit in the same point. Here, the phase always starts at 0, 0. You see, again, 0 here, 0 here, 0 here. Always starts at the same phase, which makes what's called coherent receivers, more efficient. If you pick a different choice of frequencies, the phase might start differently at a different bit. So, as you will actually see when we do the APRS implementation, they picked a not so great choice of frequencies. Okay. Nice thing about this, much like phase shift keying, is a constant envelope, right? That's great. What about the bandwidth now? Well, first of all, the bandwidth is quite high. It's the difference between these two frequencies. I mean, it occupies everything here between this range, right? And of course, because I switch between these two frequencies and the phase, although continuous, its derivative is not, then I still get some side lobes. Okay, so that could be an issue. Okay, so this is not an efficient way. By the way, in the ham community, there's two protocols. One is called RTTY, R-T-T-Y, which is text-to-text communication that uses frequency shift keying. The other one is called PSK31. PSK uses phase shift keying at a rate of 31 baud. And PSK is much more efficient than RTTY. Okay, and they have the same kind of rate of transmission. It uses the spectrum more efficiently. Once you think about, okay, so now I put 4 cycles in the low frequency and I put 8 cycles in the high frequency. I can, get them closer, right? And I can put maybe 2 cycles, right, in one frequency and then 4 in the other, or I can put 1. What's the minimum that will make those frequencies orthogonal to each other? 1 and 2 is a orthogonal frequency, but is that the minimum? Half and 1. Right? Half a cycle and 1 cycle is also can give you orthogonal, and this is called minimum shift keying. Minimum shift keying is a form of frequency shift keying that the rates are such that you've got 0.5 cycles and 1 cycle per 1 bit. Okay. In that case, for the same 2 frequencies that I picked before, now I can play 2400 bauds, okay, which is quite a higher rate. But look at my bandwidth. Right, it's not much bigger. Actually, it's even smaller than what it was before. So in terms of efficiency of using the spectrum, look, this I only have 300 bits per second, and my bandwidth is like from here to here, right? It's pretty high. But now I'm using 2400 bits per second, but this is just my bandwidth. Okay, so it uses the spectrum way more efficiently. And what you're going to do in the lab is do something else where you're going to filter the phase a little bit using a Gaussian window before you compute the frequencies, and this is called GMSK, Gaussian minimum shift keying, and that's actually the modulation that you use in GSM cell phones. Okay, and that makes all these, spikiness, and the narrowband goes a little bit away. Okay, it is nicer. Okay, any questions? Yeah.
Why is it that you have cycle, 1 cycle?
If you look at the orthogonality condition for this, you will see that they'll basically cancel to 0. Okay. If you have one cycle multiplied by half a cycle, if you integrate over that, it's 0. Okay, because half a cycle is symmetric, and 1 cycle has positive and negative lobes in it, and that would basically cancel. So those would be orthogonal signals. Does this make sense? Yeah, half a cycle is symmetric, and then when you do a full cycle, is of course multiplies the first part with a positive number, the second part with a negative number, and then it's exactly the same, so they cancel. Yes. Okay, so this is called minimum shift keying. Actually, one of the options, for example, in the project could be, changing the APRS protocol to use minimum shift keying to double your rate, because the rate of APRS is actually 1200 bits. Now you can double it using minimum shift keying without necessarily increasing your bandwidth quite a bit. Okay, so you can that's one way to transmit more data. Okay, for the same amount of time. Okay, so change your modem as opposed to compressing the image or finding other ways to send. That's one of the ideas that you can come up with, or actually take in this case because I came up. Okay, so this is the pre-lab. Okay, this basically you're just going to click and go. But I wanted you to give you some overview on this because it's going to relate to what you're going to do in the lab that actually requires you to do something. Okay, and this is Lab 6 Part A. In it, Lab 6 Part A, what you're going to be implementing is what's called audio frequency shift keying. Now, I'm calling it audio frequency shift keying because it's frequency shift keying in the audio range. Why you would even want to do this? How do you actually implement frequency shift keying on a FM radio? Like if you can control everything. Now, if you have an FM radio that can transmit, basically it's frequency modulated, right? You have some way to control the frequency, right? You have a variable frequency oscillator that you can change the frequency, right? That's how FM works, right? I speak, it changes the frequencies. Okay? So I can implement frequency shift keying by applying a constant voltage on the variable frequency oscillator that would shift the frequency to be positive. And I can apply a negative voltage, we'll switch it to a different frequency. And then I can switch between them. So basically send a binary signal of plus and minus some amplitude. And that would switch between two frequencies, right? Okay, so sending a signal which is constant through the audio port of the radio, what would happen to it? Remember Lab 5. What did you do in Lab 5? You measured the frequency response of the input of the radio, right? And what did you find out? It's a bandpass. So if I now try to send a constant, like frequency offset, and then switch to a negative, right? I'm sending a DC signal. What would happen to it? It will get filtered out. So just not possible to implement without changing the hardware using these radios. So people have said, well, okay, but I can send some AC signal in to the audio, and that will be then frequency modulated on top of it. Okay? And this is called audio frequency shift keying. It doesn't have a very efficient use of the entire spectrum because you're doing frequency shift keying that is FM modulated afterwards. So it occupies 15 kilohertz no matter what. If you're going to put a certain amplitude, that's because it's FM modulated, it's going to eventually take 15 kilohertz of the spectrum. Okay, your radios take 15 kilohertz of the spectrum when you speak. So that is not avoidable. Okay? So it doesn't have a good use of the spectrum, although you're sending a signal, switching between 1200 and 2400. So that's not a big, it's only 1 kilohertz really, or maybe 2 kilohertz. You're going to be using 15 kilohertz. So it's not an efficient use. But it's really easy to implement. You only need to do is connect your computer audio output into the input of the radio, and it will go through it, and it will be sent. So this is why it is actually used. Okay, and it's called audio shift keying to separate it from the fact that you're going to go in the radio, modify the hardware, and control the oscillator of the radio itself as opposed to driving through the audio. Okay, that's why it's called audio shift keying. Yeah.
Just to clarify the difference between the two, or at least my current understanding is that you have, like, say you're broadcasting at like 143.5, and then you just have a constant, and then you just modify that 143.5 to like 140.51, or down to 0.49.
Okay, so let's say that my radio didn't have this bandpass filter. Okay, and it's FM modulating my signal. If I would send, and let's say 1 volt in the input will translate to a 1 kilohertz offset. I could send 1 volt plus, 1 volt minus, and that would, in the spectrum that's being transmitted, would be translated into 1 kilohertz up and 1 kilohertz down. Overall, 2 kilohertz range, kind of, right? But of course, because it's switching, it's a little bit more than this. It's going to plus the bit rate. Right now, what I'm doing, so it's not possible, though, to do this. I have to send AC. Right? So what I'm going to do now is I'm going to send frequencies, 1200 hertz and 2400 hertz. But this is kind of like a constant signal, right? Constant amplitude that will be translated into a full span of the of what the radio is going to be transmitting. And if the radio is set to transmit the deviation to be 15 kilohertz, that's what's going to be transmitted. Even though I'm only switching, even if I sent a constant tone, that will be sent as 15 kilohertz. If I send speech, it's 15 kilohertz. Whatever I send, it's always 15 kilohertz with FM. Because the amplitude is translated into, I can send lower amplitude, but then I'm going to be more sensitive to noise. Okay? Does this make sense? A little bit? So we're going to implement audio frequency shift keying. So it's implemented in the audio frequencies. And what you're going to do is implement basically a modem for packet-based transceivers. Okay? You're going to send packets, short packets, using audio frequency shift keying. Okay? In part B, so this you will implement the modem. So the transceiver, the transmitter, and the decoder. And in part B, you'll use this modem to implement the almost the full-scale automatic positioning reporting system, where you will actually construct packets according to a certain protocol. It's not just sending bits. The modem lets you send arbitrary bits. APRS is a protocol that you're going to send, bits with the address, where to, and where it's going, and there's a payload, and then there's some error correction, all built into a packet. And then so it's kind of like it's a link layer protocol. So it's not the physical layer that's the modem. You think about the network layer. Who took 122? So there's the physical layer, and then on top of that, you're going to build the link layer, which you'll be able to send packets of data and interpret them appropriately. Now, because other systems built by amateurs also use this APR system, you'll be able to interact with them too. They'll know how to decode your packets. And so you'll be able to, for example, send a packet that will tell a receiver to send you an email back, okay, if you construct the packet accordingly. Or report your position on aprs.fi with putting an icon with your call sign at your position that you're reporting. Okay, so you'll be able to do this. I think I will give you an option to put yourself on Everest, okay, with the coordinates on Everest. But don't abuse this too much. Okay. You will also be able to send packets to classmates and decode them. Okay, and we're building a GUI for you to just easy to enter things in, and so you'll be able to. It will just be easy to. You'll just hook into that GUI and use that in order to activate your implementation. Yes. And you'll be able also to pick up packets. So the International Space Station has an APRS repeater on board, packet repeater on board. And I recorded a pass of the ISS, and you're going to be decoding the signal picked up from that station. There's also, I'm going to put an antenna that we built in my other class that I teach on ham radio. It's a Yagi antenna made of measure tape that you'll be able to borrow, and if you want to record signal from the ISS yourself, you'll be able to do that. You just connect it to your radios and be able to pick up signals from ISS and decode them. And if you really want to, you can also transmit and relay packets through the ISS to other amateurs. Okay? And you know if you're successful because it's aggregated through internet links. If actually a pass is DGP'd through the ISS, it will be reported online too. So you'll be able to see whether you were successful or not in transmitting through ISS. I was successful once. So, with the Baofeng radios that you have. Okay. Well, I'm running out of time, huh? I like to talk a lot. Okay, so you're going to implement what's called AFSK 1200, which is also the standard for Bell 202 modem. It's really one of the old modems. Back in the days when you use your phone in order to connect to some things. Bell 202 modem. It encodes digital data at 1200 bits per second. Uses audio frequencies of 1200 and 2200 per choice, because it doesn't start. The phase doesn't start. Doesn't reset every bit. So it is within the bandwidth of the audio input bandpass filter of your radios, and that's the advantage. It's still very popular for ham packet networks like APRS. And the way you're going to encode it is you're going to construct a signal called MT, M of T, M as a function of time, of pluses and minuses. Okay? And you're going to construct it by basically integrating that signal into this framework where you have a 2pi FC. That's the FC is 700. That's the middle frequencies. 2pi delta F. Delta F is 500, so it's either 500 plus or 500 minus. And you're basically going to integrate over the phase. Okay, so integration of the phase gives you the frequency. The derivative of the phase gives you the frequency. And so now you're going to construct basically the frequency by integrating it. Okay. So if you take the derivative of this, really, the derivative of this is 2pi FC plus 2pi delta F times M, which is exactly what you want. Either plus 500 or minus 500. Those are the frequencies. But the nice thing about this is guarantees that the phase is always continuous. Okay, so it's not going to start every bit at the same point, but it's always going to be continuous. So you're going to get a nice spectrum. You're going to write that kind of modem. The modem writing is pretty trivial. You need to take care. Sampling rate 44 kilohertz doesn't divide with a bit rate. So you'll have like n plus 0, some partial bits, number of bits. N plus some partial of samples per bit length, which is a problem. So what you're going to do is you're going to construct the entire message at 4 times the rate and then downsample. Turns out the exact rate is the 44.1 multiplied by 4 does divide with the bit rate. So you're going to first construct it at 1600 kilohertz, and then you're going to downsample. When you look at the spectrum, it looks like this, of random bits. And then you're going to build 2 decoders. One is a non-coherent decoder. You're going to pass the signal through 2 bandpass filters, one centered around 1200 hertz and one centered around 2200 hertz. These are complex filters that we're going to detect the envelope, effectively. It's an envelope detector. Complex at 1200, complex at this. You're going to take the absolute value, and then you're going to subtract the 2 signals. When the transmitter sends this signal, then that's going to be high, and this is going to be 0, so you're going to get a high value. When this tone is transmitted, then this is going to result with a 0. This was going to result with a high, and so you're going to get a negative signal. Right? That's how the bits are going to be transmitted. This is the result of extraction from this point, and you kind of see the bits. And then what you're going to do is you're going to take the signum, right, the sign of this, rectify the signal to say it's either a 1 or a 0. If it's positive, that means it's a 1. If it's negative, that means it's a 0. And then that's going to give you back this plus minus, right? That's the signal. The other demodulator you're going to build is an FM demodulator. If you think about this, is exactly the same equation for FM, right? If that was S of T, in FM, that was exactly the thing. But now your message is just plus minus 1. So you can actually implement the same thing as an FM demodulation. And what you're going to do is you're going to filter the entire signal with a complex filter and then look at the phase of it. If the phase is positive, then it means that it's a 1. If the phase is negative, then it's so on and so forth. Okay? So you're going to do that too. Then you're going to add noise and see how it behaves with noise. And you see that you see bits here. This is binary, but now it's noisy. The cool thing about it is if you actually cut a line here, you can still decode the bits exactly. You're going to compute then what's called bit error rate. What is the rate that you're going to make mistakes with different noise level? In this case, the rate was 0.0021. Okay? Bits were actually wrong. And then you're going to compute this bit error rate versus SNR for the two type of demodulation. So you're going to add more and more noise, and you're going to see that at really good SNR, you have a very low error rate. This is a low error rate. Beyond that, you're almost always successful. And then as you add more and more noise, this is poor SNR, you're going to get more and more wrong. Up to 50% of the time wrong, which is this point, which means they have no information. Okay? So this is what you're going to do in the lab. This is lab 6 part A. Lab 6 part B is taking whatever you've done and integrating that into a full transmitted receiver that you be able to run an application with. Okay? Sounds cool? See you on Friday.